Okay, so let's continue from last week's lecture, which was, sorry, last lecture, which was this Monday. So we started with pack learning. Just to recap, with pack learning, we want to figure out how badly does our model perform on data sets that was not used to train the model. Okay, so we saw last time an analogy of an urn or a pail of marbles. There are infinite marbles in that pail, and they have two colors, green or red. So the green marble represents, the correct observation. The red marble represents, incorrect observation. And what we have is we want to randomly picking these marbles one by one. And as you saw in the last lecture, that as the number of time as you pick them, keep on picking the marbles, the error or the number of, the average number of, marbles that you see, mu, which is a probability that the marble is red, is it converges to that value. So as the number of times, which is n, increases, the probability almost converges to the actual mean of error, right? So we want to figure out how many times do you actually need to pick, and does it work for the general case of general hypothesis set, because in that particular case you're fixing the hypothesis. So the marbles are colored red or green for a particular hypothesis, but can this be extended to other types of hypotheses? So that's the question that we're trying to answer. So we saw last time that the average error, let me just go back and recap. So the average error that we see here, the average number of times you'll find the error is it's mu. So this is the actual average. Okay. So n. So as you increase the number of as you draw samples, it doesn't matter. N doesn't affect mu here. But then when you go to the variance part, how much is there spread in the actual the observation that you see? So from the true error, so it's sort of like proportional to 1 over n. We saw that. So as n increases, then this distribution becomes more narrow and more concentrated around the true mean, right? So it's true error. So as n goes to infinity, then you can expect to see something like this, so something that's more clustered, right? So there's less variance. So which means that n plays important role in understanding what the actual error is of your model for a particular hypothesis that you've selected. So now recapping that, so we have this. So variance is an important tool as well. So okay. So what we want to find is what's the probability that the error that you actually observe from the outsample points is actually close to the true mean, right? So Vn minus mu. So what's the probability that Vn minus mu is greater than an epsilon? Okay, so let me explain to you this term one by one. So with this term here, Vn, so this is our observation. Okay, so if you select endpoints, if you draw endpoints from the pail, and what's your observation? On average, what's the proportion of times you pick the red marble? Okay, this is the error that you observe. Observation of error as you pick n marbles. So error in this case is the red marble. Okay, and what is this? This is the true error, right? The true error. So for any observation, any outsample points, this is the actual error, mu. And what you want to find out, what's the probability of this difference between the actual error and the observed error, So this is sort of like in-sample error, and this is sort of out-sample error. Okay, that's the analogy. So what's the difference between these two? When will it become above epsilon? So this is the difference in the true error or outsample error and in-sample error. So when does it become above this quantity? So that the probability of you computing the in-sample error and it's larger than epsilon than the actual error. So this is pretty cool because you don't know what mu is, right? Mu is unknown because this is a target function. But if there's a way to compute this probability of how far the actual error is from the in-sample error, then you can figure out how well your model performs on points that are outside of the training set. So that gives you a lot of information. But how do you actually compute it? So, there is this inequality, which is called the Chebyshev's inequality, okay, that we can apply, which states that this probability is bounded by the variance of the in-sample error divided by epsilon squared. So the variance of the in-sample error has been computed from the previous case. So we saw that if it's a Bernoulli random variable, then it becomes mu multiplied by 1 minus mu over n, which is once again bounded by 1 over n. So you substitute that. So this is obviously bounded above by 1 over n divided by mu epsilon squared, which is equal to 1 over n epsilon squared. So this is pretty nice because if you have, so you can figure out how often does your in-sample error become larger than the out-sample error by epsilon, and that probability is bounded above by 1 over n divided by epsilon squared. So this is pretty interesting. So there are two things that are governing this relation. First thing is we have this term epsilon. So this is the margin of error of difference between in-sample and out-sample. So in-sample is Vn, out-sample is mu. So if you want to have a lower bound, the lower margin of error, then you see that 1 divided by a small fraction becomes a large value. So the probability of this, the gap between the in-sample and out-sample error will actually go up as you decrease the margin because it's less likely, right? That's the idea. But if you increase n is a whole number, right? It's an integer because it's a number time you draw the samples. So as n goes to infinity, you can see that the probability actually goes down of going outside of this gap, okay? So pictorially, what we want to do is figure out, so this relation here, let's write it again. This is a probability of Vn minus mu being greater than epsilon, or Vn minus mu being less than negative epsilon. So I'm just like breaking this absolute value into two parts, okay? And if you try to sketch this, what you get is a curve like this. So if this is mu, so what you will observe is that if you try to plot these values, so if you know the true mean, you'll know that. So let's plot this curve. Okay, so if this is the gap. This is mu minus epsilon. So this is the gap that you are allowing. So from the true mean, you want to find out what's the probability of being in this range. So this is Vn, right? So when will Vn be within this gap? So it's close, right? So this is Vn minus mu. It's absolute value because you're looking at both sides, plus minus epsilon. So when will it be in this gap? And that's dictated by this equation here. So it will be within this gap or out within this gap with the probability 1 minus, that relation there. So when it will be outside is what we are computing. This is probability of this red part, right, is going to be it's at least 1 over epsilon squared because it's an upper bound, right? So this gap will, the probability of this point falling outside of this gap will decrease if n goes to infinity, okay? So if n goes to infinity, then this gap, the probability of bad event, so the bad events is essentially Vn minus mu being greater than epsilon, is going outside of the margin, is lower. But if you fix n and you decrease the gap, right? So if you want to make this gap smaller, so smaller means you're going to make it small like this. So if the gap becomes smaller, then the probability of bad event is higher because you're dividing because 1 divided by n times a very small number, say 0.001, is obviously pretty big, right? So this is what you have to play with. So if you want to be absolutely sure that your in-sample error is close to the out-sample error, then you have to either draw lots and lots of samples, which is not all, we don't always have that, right, in our training set or test set. Then we run into the problem of having a loose gap, right? So there's a significant gap. But if you have a large number of points and you want to have a smaller margin, then that's possible because there's a sort of trade-off between the two. So what does this all mean? So let's say that, delta is the probability that your in-sample error is within the confidence interval. So what I mean by the confidence interval is that it's between, you're between these values, mu plus epsilon, or you're in this gap. So let me just write it properly. So it's going to be mu minus epsilon and mu plus epsilon, this interval. So this is where the error is. So this is the confidence, right, interval. So that's delta. And so the confidence level is defined to be 1 minus delta. This is the confidence level. It's different from interval. So suppose that you want this probability of your error, in-sample error, to be within the confidence interval, to be 0.01, then the confidence level is 1 minus delta, which is 0.99. So this implies that you want to be 99% confident that your in-sample error is close to mu within some margin. Okay, so this is called the confidence level. So confidence level. Okay, so what does that mean in terms of the margin? So we have an equation, right? So we know that from the Chebyshev's equation, the probability relationship, we know that the probability of it being the error, the in-sample error being outside of this confidence interval is governed by 1 over n times epsilon. So this probability is Vn minus mu being greater than epsilon is governed by 1 over n epsilon squared. So you know that if you fix this, if you want this the probability of it going outside, you want to fix it to a value, say 0.01. So this is going to be, my apologies, as Vn is not in the confidence intervals, it's outside. Okay, so if you want to fix this value to 0.01, delta equals 0.01, then what will epsilon be for a fixed n? So you can make that computation here. So you can see that when you say solve for delta is less than or equal to 1 over n epsilon, then you can solve for epsilon. So epsilon, if you know what you want this delta to be, then you can figure out that if you can just solve for epsilon by rearranging this equation. So you have 1 over n delta, and then you have its square root. So this is one relation that's quite useful because it tells you about the confidence interval. So you now know that the confidence interval is going to be the true error minus, if you have if delta is 0.01, then it's going to be 10 over n, and then mu plus square root of n. So this is the error when the interval when delta is equal to 0.01. So when you plot it, you get, let's plot this. So as n increases, and this is actual mu, there's 99% chance. So if you plot this equation with respect to n, this interval with respect to n, and this is mu, this axis is mu, then what you get is you have a relation that's 1 over n, square root of 1 over n, that looks like this. Okay, so if you fix n at this value, so this is the gap between mu and around the true mean, and this is going to be mu plus square root of 10 over n, and this is mu minus square root of 10 over n. And what you see is that as n increases, this gap goes almost to 0, right? So if you fix n, then this is the distance, then you are 99% confident. So what this implies is that there's 99% chance that your true error is different from the in-sample error by this much value. Okay, so now we have sort of this error bound, right? But can we do better? Can we have a tighter bound? So like this is an upper bound, right? So as you can see, the Chebyshev's inequality gives you an upper bound, but we want something even more tighter. So obviously there's a lot of slack, but can we reduce the slack from the actual difference? So that's the next question. So for that, we'll be using something called the Hoeffding's inequality. So with so the question is, again, so the gap between the true error, which is E out, and in-sample error, which is E in. This is all with respect to a particular function, a particular hypothesis, right? So with respect to H, is bounded by 1 over n epsilon squared using the Chebyshev's inequality. So it's an upper bound. So what I mean by that is that if you plot the actual values, so this can be mu again. So the Chebyshev's inequality may have computed some. So you know that this is the gap between the actual and true error, but this is an upper bound. So the actual gap might be something that's even smaller, like this. So that this gap is sort of a slack, right? So can you make this bound, this gap, even more tighter? That's the next question. So can we do something like that that's more closer so that you actually get the real idea of what's the actual difference between the true error and the in-sample error. So you want to tighten the gap, right? So that can be done using another inequality called the Hoeffding's inequality. So the Hoeffding's inequality is defined to be this. So I need a tighter gap to get a better idea, a better or more realistic idea of the actual difference. So Vn minus mu. What's the probability of going out of this interval? So you want to get a even more tighter upper bound for the probability. Okay. So the Hoeffding's inequality can be used here, and it's defined as follows. It's going to be the probability that the difference between the in-sample and the outsample error is above epsilon is bounded by 2 times e to the power of 2n epsilon squared. So this bound is actually much more, it's exponential, and it's actually decreases much faster. It's more tighter than 1 over n epsilon squared, because this is, so when you plug it in, you can see that e to the power of negative 2 n epsilon squared goes down faster than this. So obviously this is a more tighter bound. But how do you actually apply it? So there are some conditions. So the Hoeffding's inequality only works, applicable for IID Bernoulli random variables. So we make that assumption that we're fixing the hypothesis. So when you fix the hypothesis, that means that there's no sort of dependency on the data that you're drawing. So in that case, this IID assumption works. But then it's not true when you consider a whole bunch of hypotheses that are trained using the training data, because there's an automatic correlation occurs there. So then it doesn't really apply when you look at the entire hypothesis set, right? This assumption. But let's just assume that it does hold. So we're fixing this is true when you fix the hypothesis set to be a single hypothesis. Okay, so let's just say that we fix it to one particular hypothesis. So we assume some set of random weights. We don't train them using the training set. Okay, so then once again, if you let the delta to be less than 2 e to the power of negative, so this is the confidence, right? And you solve for epsilon. So you want to see how well, what's the relationship between n and the margin epsilon, because this is now going to be the probability that Vn minus mu is greater than epsilon. Okay, so let's say this is delta and this is bounded above by 2 times e to the negative 2. This is where we come from. So when you solve for epsilon by rearranging the terms, you get epsilon is bounded above by 1 over 2n ln of 2 over delta to the power of 1 over 2. So when you plug this in, so when delta is equal to 0.01 then epsilon is going to be 1.63 divided by square root of n, in the original Chebyshev bound, and with the other bound you can plug it in. You get no, sorry, so this is not Chebyshev. This is actually what you get when you plug it in to the Hufting's inequality. And this is, so we saw last time that we had a different value. So when, you know, so this is with the Hufting's inequality, and with the Chebyshev's inequality we get epsilon is less than square root of 10 over n, and this is larger than this, right? So when you plot it, what you get is that so this is mu, and as you increase the sampling, Chebyshev will have a upper bracket like that, and Hufting's inequality gives you a much lower bound. So this is the gap, 99% confident of being within this distance of the actual mean error. So this implies that Hufting's inequality is way much better or tighter, because it gives us a better idea of how close it is actually. So let's switch the notations from Vn to mu, and mu to E out and E in. So this implies that E out, so we had probability that Vn minus mu is greater than epsilon, right? So E out minus E in is greater than epsilon. It's what we want to figure out. So this is outside of the margin, but if you want to compute when is it within the margin, then you'll change the sign. So when is the true error, the difference between the true error and in-sample error within epsilon? Okay, is what we are computing here. This is what we're getting here. So when you plug in these values, you know what epsilon is. So this is going to be square root of 1 over 2n log of 2 over delta. So when you substitute it, so we have E out minus E in is less than epsilon. Okay, so epsilon is going to be that term over there, square root of 1 over 2n log of 2 divided by delta. And what this implies is that E out is less than or equal to E in for a particular hypothesis, because remember, it only holds this IID Bernoulli thing only holds when you fix a hypothesis. So the error is going to be above by square root of 1 over 2n, or below for the other side. So this is a nice result because it tells you exactly how this is the distance from, so if you have the in-sample error, the outsample error, this is the distance. The in-sample error from the outsample error at maximum, right? This is sort of an upper bound. Okay. But like I said, if you have to fix the hypothesis, and this is not the case because we change the hypothesis based on the training set, right? So you have to note that the Hufting's inequality applies only when the random variable z1 to zn are IID. So these are the marbles that you draw from the pail. And is this the case? So z1 equals, essentially finding the indicator variable. So is it equal to the observation of x1? So H is your hypothesis, and your model tells you something, and your observation is something else, so that when it's not equal, you see the red marble, right? And then you do it for the second sample, which is why you substitute x2, and so on up to zn, which is h of xn. So we see that, yes, one by one, if you fix h to be a single value, single hypothesis, then it is IID. So if h, which maps the input space, real space, to discrete value, and it's fixed, is a fixed hypothesis selected by observing D, then yes. Then what that means is that CIs are IID. But this is not typically the case. Why? Because the issue is, in practice, this is not the case, as H is trained using D, which is a training set. So you actually trained after observing D. So you're not randomly drawing, but rather you're seeing what D is, and the parameters change in basically what D had, the content of D. So because of that, there's a dependence, right? It's not IIDs, it's actually dependent. But since in this section we are considering a finite number of hypotheses, so that's what I said, M is finite. So H is a set of hypotheses where you fix the parameters for M different, like say for example, if you're looking at the perceptron, you have fixed weights, M different fixed weights, and then those are the M hypotheses you have. And the best hypothesis is G, that belongs to the set H. So G is one of H1 or HM and so on. So then for E in minus E out, the difference, the gap between the in-sample and out-sample error, we saw for the best hypothesis is this. It's going to be either the error for the first hypothesis, the in-sample error for the first hypothesis minus out-sample error for the first hypothesis, or the in-sample error for the second hypothesis and out-sample error for the second hypothesis, all the way down to the in-sample error of the mth hypothesis minus E out of the mth hypothesis. So this error, the best hypothesis, the error is either one of these, right? So the gap. So as G belongs to the set H, the event pertaining to G is a subset of the above. So subset of, essentially, so this is the error of the best hypothesis. Okay. So this is going to be a subset of the union, so combination of all the other events of I equals 1 up to M. So there are M different hypotheses, and essentially it's a union of the in-sample error of the ith hypothesis minus the outsample error of the ith hypothesis, right? And so if you apply the probability, you get the probability of the in-sample error minus the outsample error for the best hypothesis is going to be, less than or equal to the probability of the union of these other events, the error of individual hypotheses in that hypothesis set. And we know from probability that, so this is a union bound. So aside, you know that the probability of two events, the union of two events, is the probability of one event A plus the probability of the second event minus the intersection of these two events. So if you ignore this, then this becomes an upper bound of the summation of individual events, right? So what happens is that when you go back, you get the probability of the best hypothesis having a gap of epsilon is going to be bounded above by the probability of individual events I equals 1 to M, the probability of E in of HI minus E out of HI. Okay, so this is how we get rid of the union sign, which summation is an upper bound of the union of all events. So this is called the union bound. And when you substitute the values for individual probabilities that we've got from the Hufting's inequality, so substituting upper bound from Hufting's inequality, you get the probability of E in minus E out for the best hypothesis. It's going to be bounded above by the summation I equals 1 to M 2 times E to the power of 2n epsilon squared, but there's no I within this summation. So what you can do is this is equals to 2 times M is the number of hypotheses, times e to the power of negative 2 n e epsilon squared. Okay, so this is an interesting result because now the probability of being how close it is to the actual mean, in sample and outsample errors, is dictated by this term here, which is a function of the number of hypotheses, so i.e. model complexity. This reflects model complexity. So the more hypotheses you have, the more complex your model is, and n is the number of samples in the in-sample error. Okay, so we can clearly see there is sort of a weakening. So the more hypotheses you have, the more loose your bound will be, right? Because from here you can see greater the number of hypotheses, the more is the likelihood of error, of not being close to the actual mean. So what is M? What is M when the hypothesis set is general perceptrons? So hypothesis set is defined by the sign of W transpose X plus some offset B. And you're going to figure out this W can take anything, any values in the real space. So here M is infinite because you can have any infinite number of combinations of W. So when M goes infinity, then this error bound is very loose. So you can't really do much when you have highly complex hypothesis set, and just the basic one that we know has an infinite M. So this Huffington inequality doesn't really work well, but it gives us some insights on how model complexity affects the bound, the error bound. So now we have delta, which is a confidence level, to be 2 times M times e to the power negative 2n epsilon squared. So now when you solve for epsilon, you get square root of 1 over 2n log of 2m over. So this is a relation you can derive. So the generalization error. So that in general, how does your in-sample error compare to out-sample error is dictated by delta G, which is the difference between for the best hypothesis, E in minus E out. So the difference, how different they are, is bounded above by square root of 1 over 2n log of 2m over delta. So this implies that E out, the outsample error, is smaller than E in, the in-sample error, plus this sort of gap term, so log of 2m over delta, and this m is a problem. Model complexity, this is the samples. These are two things that you need to watch out for. So how does our system, how is it affected by m and n? So just by observing this bound, you can reach to some conclusions. So n is the number of training samples, and m is the number of hypotheses. Okay. So when you plot it, you have m. If m is a large value, becomes higher, or n becomes higher, how does it affect the gap between the in-sample and out-sample errors? And how does it affect the training error? So as you increase model complexity, it's intuitive that the in-sample error goes down, but the gap is obviously going to go up because of this term here, m. But when you increase n, the training samples, then because n is in the denominator, this gap goes lower, but the in-sample error, if you fix m, but you still increase m, it isn't really affected too much, right? So this in-sample error goes up because m is fixed. You need to, if m, so this is in the other case, right? If m goes down and n increases, so that's when we have this trend here. So what we want is more specificity in the model. So if you plot this relation, so you have E out, I'm just gonna write it again just for ease of reference. E out of G, E in G plus square root 2n log of 2m over delta. So let's have two plots, one where you fix m and the other where you fix n. So there are two plots. So in this plot, you're fixing n. So you're changing the model complexity, the number of models you have. And this is the error, the gap, okay, or the actual in-sample out-sample error. So what we'll see when you plot this is that the error the outsample error is going to increase like this. So let's do the in-sample error first. This is the in-sample error. So as the model complexity increases, the in-sample error will go up, down, because it's more specific, right? So if you have points like this, then if you're very specific, if you have a very specific model, you'll learn it like that, right? But then now if you have the outsample error, we know that it's going to go down and sort of come up like this, right? And this change, this difference in the error is going to go up. So this is going to be delta G, and this is going to be E out. So that's what we are using. So delta G is proportional to square root 2n log of over delta, and you're fixing this, right? So this is essentially a log function. So that's how we got this trend in the beginning of this lecture, or the previous lecture. And then if you plot the same curve for fixing m, fix the model complexity, and see how the error is affected. So you're changing n with so how does the gap change with n? Once again, you have E in is going to go down the error as you have more training samples, and we have the gap between the two. It's going to be like, this is going to be delta G, that's proportional to so let's just say it's 1 over square root of 2n, because the other term, log of 2m divided by delta, is a constant. When you sum it up, you get the outsample error, which is once again has this sort of trend. So in both cases, you can see that the best m will be right here, and this is the best n. So if you have too many training points, then you're overfitting, right? So as you go further like this, overfitting, and if you go further like this, it becomes too specific. So you want to avoid both cases. So there are two issues. So we now have a general trend, but it only applies to a finite number of hypotheses. So more refined analysis is needed for m equals infinity, which is generally the case because you don't have a select number of hypotheses. Okay, so that we'll look in the next week's lecture. All right, so that's it for this week.